Distributed Systems from Scratch. This is episode 20, Distributed ML Systems. By the end of this episode, you will know how a model that cannot fit on any single computer on Earth gets trained anyway, and why the answer is essentially every protocol in this series running at once. GPT-3 has 175 billion parameters. Training it required 355 GPU years of computation, running thousands of GPUs for months. No single machine can do this, not even close. The challenge of training modern AI models, the largest engineering effort in computing today, is fundamentally a distributed systems problem. How do you coordinate thousands of GPUs to train a single model? How do you synchronize their work? How do you handle failures during a weeks long training run? Every concept from this series applies here. There are two reasons to distribute training: data scale. Modern models train on trillions of tokens. A single GPU processes one batch in a few seconds. The full dataset would take months on one device. The solution: split the data across GPUs. Each one trains on a different batch simultaneously. Model scale: a 175 billion parameter model needs roughly 350 gigabytes just to hold the weights in half precision. Now add the gradients and the Adam optimizer state, momentum, variance, and a full precision master copy of the weights, and training needs about 16 bytes per parameter. That's nearly 3 terabytes of training state. A high-end A100 GPU has 80 gigabytes. The model doesn't just not fit, it misses by a factor of 35. The solution: split the model across GPUs. These two needs drive two different parallelism strategies, and in practice, large training runs use both simultaneously. There are three forms of parallelism in distributed training. Data parallelism: the same model on every GPU, different data on each. Scale training speed: model parallelism: different layers of the model on different GPUs, fit models that are too large for one GPU. Pipeline parallelism: models split across GPUs, but with micro batches overlapping to reduce idle time. Let's go through each one. Strategy 1: Data parallelism. The simplest and most common approach. Same model everywhere, different data on each GPU. Here's how data parallelism works. You have three GPUs, each holding a complete copy of the model. The training data is shuffled and split into batches. GPU 0 gets batch 0, GPU 1 gets batch 1, GPU 2 gets batch 2. Each GPU independently runs forward pass and backward pass on its batch, computing local gradients. Now, the critical step: all reduce. All three GPUs synchronize their gradients by averaging them. GPU 0's gradients, GPU 1's gradients, and GPU 2's gradients are combined into a single averaged gradient. Every GPU then applies this same averaged gradient to update its model weights. Since they started with identical models and applied identical updates, the models stay in perfect sync. Repeat: next batch, forward, backward, all reduce, update. Ideally, n GPUs give you n times the training throughput. In practice, the bottleneck is gradient synchronization, the all reduce step. The all reduce primitive is the heart of data parallelism. The standard implementation is ring all reduce. Arrange the GPUs in a logical ring. Each GPU splits its gradient into n chunks. In the first phase, scatter reduce, each GPU sends one chunk clockwise to its neighbor, receives a chunk from its other neighbor, and accumulates. After n-1 steps, each GPU holds one fully reduced chunk. In the second phase, all gather. The reduced chunks are propagated around the ring, so every GPU ends up with the complete averaged gradient. Total communication: 2 times n-1 messages. Bandwidth optimal, no central server bottleneck. Each link in the ring sends the same amount of data regardless of the number of GPUs. This is why ring all reduce replaced the older parameter server approach. It distributes the communication load evenly. Strategy 2: Model parallelism. When the model doesn't fit on a single GPU, split the model itself across devices. Naive model parallelism is simple. Assign different layers to different GPUs. GPU 0 holds layers 1 through 16. GPU 1 holds layers 17 through 32. GPU 2 holds layers 33 through 48. Data flows sequentially. Input goes to GPU 0, which computes its layers and passes the activations to GPU 1, which computes its layers and passes to GPU 2. The problem is obvious. While GPU 0 is computing, GPUs 1 and 2 are idle. While GPU 1 computes, GPU 0 and GPU 2 are idle. With 4 GPUs, utilization is only 25%. Three quarters of your expensive hardware is doing nothing. This idle time is called the pipeline bubble. It makes naive model parallelism very inefficient. Strategy 3: Pipeline parallelism. The fix for the pipeline bubble. The insight: split each batch into smaller micro batches and feed them into the pipeline one after another. GPU 0 processes micro batch 1 and immediately passes it to GPU 1. While GPU 1 processes micro batch 1, GPU 0 starts on micro batch 2. While GPU 2 processes micro batch 1, GPU 1 is on micro batch 2 and GPU 0 is on micro batch 3. After the warm-up phase, the initial bubble, all GPUs are active simultaneously. Each one is processing a different micro batch at a different stage. There's still a bubble at the start and end of each batch, but with enough micro batches, the bubble becomes a small fraction of total time. Google's gpipe and Microsoft's Pipedream pioneered this approach in 2018 and 2019 respectively. There's a fourth strategy that works at an even finer granularity: tensor parallelism, introduced by NVIDIA's Megatron LM. Instead of assigning whole layers to different GPUs, tensor parallelism splits individual layers. A single transformer layer has weight matrices with dimensions like 12,288 by 12,288. You split the columns of this matrix across GPUs. Each GPU computes its portion of the output, and the results are combined with an all-reduce. This works best within a single machine, where GPUs are connected by NVLink, a high bandwidth, low latency interconnect. Across the network, the per layer all-reduce would be too expensive. Tensor parallelism has a smaller bubble than pipeline parallelism because there's no sequential dependency between stages. All GPUs compute simultaneously within each layer. In practice, frontier model training uses all three strategies simultaneously. This is called 3D parallelism, and the diagram shows the whole thing. Zoom into a node first. 8 GPUs connected by NVLink, all working on the same layer. That's tensor parallelism at the tier with the highest bandwidth. Now zoom out one level. Node 1 holds layers 1 through 24. Node 2 holds layers 25 through 48. Activations flow down over InfiniBand. That's pipeline parallelism across nodes within a rack. And finally, the widest view. Rack 2 is a complete copy of Rack 1's pipeline, chewing through different data. The two replicas synchronize gradients with all reduce over standard networking. Data parallelism at the cheapest, slowest tier. Notice the pattern. Each parallelism dimension is matched to the bandwidth of its communication tier. The chattiest traffic rides the fastest links. This is how GPT-4, Palom, and Llama were trained. Thousands of GPUs, three nested levels of parallelism. The fundamental bottleneck in distributed training is communication. Consider the numbers: 175 billion parameters times 4 bytes each equals 700 gigabytes of gradient data that must be synchronized every single training step. Several techniques reduce this cost. Gradient compression: send only the largest gradients or quantize them to fewer bits. Lossy but dramatically less bandwidth. Mixed precision training: compute in half precision, FP16 or BF16. half the memory, half the communication bandwidth, and faster computation on GPU tensor cores. A master copy of weights is kept in full precision for stability. Overlap communication with computation. While the GPU computes gradients for layer n plus 1, send layer n's gradients over the network simultaneously. Don't wait for all gradients before starting communication. Training a large model takes weeks. With 10,000 GPUs, the failure math from episode 10 applies. At 99.9% per GPU uptime, you expect a GPU failure every few hours. Without checkpointing, a failure after 2 weeks of training means starting over. Weeks of computation, hundreds of thousands of dollars in GPU time lost. The solution: periodic checkpointing. Every end training steps save the full model state, parameters, gradients, optimizer state to distributed storage. On failure, restore from the last checkpoint and resume. Elastic training takes this further. The system can dynamically shrink or grow the GPU pool without restarting. A failed GPU is removed, the work is redistributed, and training continues. Torch Elastic and RayTrain support this. Let me name the real systems. PyTorch DDP, Distributed Data Parallel, from Meta, Ring, all reduce with automatic overlap of communication and computation, the most widely used. Horovod, originally from Uber, now a Linux Foundation project, framework agnostic data parallelism, makes multi-GPU training as easy as adding a few lines of code. DeepSpeed from Microsoft, the most comprehensive, implements 3D parallelism plus zero optimization, used to train many of the largest models. Megatron LM from NVIDIA, the reference implementation for tensor plus pipeline plus data parallelism, designed specifically for training very large transformer models. RayTrain from Anyscale, elastic data parallelism with built-in fault tolerance. JAX with XLA from Google, a compiler-based approach where XLA automatically partitions computation across TPU pods using SPMD, single program, multiple data. Let me highlight Zero Redundancy Optimizer from DeepSpeed. It's one of the most impactful ideas in distributed training. The insight: in standard data parallelism, every GPU stores a full copy of the model parameters, the gradients, and the optimizer state. That's threefold redundant memory across every GPU. Zero Stage 1: partition the optimizer state across GPUs. Each GPU stores only 1/nth of the optimizer state, 4 times memory savings. Zero Stage 2: also partition the gradients, 8 times memory savings. Zero Stage 3: also partition the parameters themselves. Now memory scales linearly with the number of GPUs. With Zero Stage 3, you can train a model that's n times larger than what fits on one GPU using pure data parallelism. No model parallelism needed for many model sizes. The communication cost increases. You need to gather parameters before each forward pass, but it's often worth it for the simplicity. Let me connect this to the series. AllReduce is the gradient synchronization primitive, conceptually similar to Gossip from episode 12, but structured and synchronous rather than probabilistic. Data parallelism is partitioning from episode 9 applied to training data. Split the data across workers. Same concept, different domain. Checkpointing for fault tolerance is the same idea as Flink's Chandy Lamport snapshots from episode 14. Save consistent state, periodically restore on failure. The failure arithmetic: 10,000 GPUs failures every few hours is the same calculation from episode 10. At scale, failure is the steady state, and pipeline parallelism is a data flow graph, like Flink's operator pipeline from episode 14, but for neural network layers instead of stream operators. Let's recap. 1. Data parallelism. Same model everywhere, different data. Ring, AllReduce synchronizes gradients, the default strategy for most training. 2. Model parallelism splits the model across GPUs. Naive approach has pipeline bubbles. Pipeline parallelism fills them with microbatches. Tensor parallelism splits individual layers. 3. 3D parallelism, tensor plus pipeline plus data, is how frontier models are actually trained across thousands of GPUs. 4. Communication is the bottleneck. Gradient compression, mixed precision, and overlapping communication with computation are essential. 5. Zero partitions optimizer state, gradients, and parameters, achieving linear memory scaling with pure data parallelism. Next episode, open research problems, the questions the field hasn't answered yet. What are the unsolved problems in distributed systems? Where are the PhD worthy research directions? We're approaching the end of the series. That's episode 20. Distributed ML systems, the most extreme application of distributed systems today. Next time, open research problems. Thanks for watching.